chapter 8. And there is like a conceptual question here, sign of the energy. Is it possible for gravitation potential energy of an object to be negative? Yes, because it depends on my level. Then I will say, if I will have, let's say, a ball that is sitting somewhere, a ball sitting here, and this is my UG equals 0, then I will say, I will consider this as my Y, which is above. Then here I will say my gravitational potential energy can be positive. But what if I decided like the highest point is going to be my UG equals 0? Then you're going to find that the position of it is going to be below my reference, and this is going to make it negative. Remember that this will not cause any problem for us when we are dealing with conservation of energy, because what I am interested always is the change in UG, not UG itself. Okay? And here it has been explained for you how it is measured relative to some arbitrary reference level where potential energy equals 0, and I can make my reference anywhere. Now you and your friend both solve a problem involving a skier going down a slope. Starting from rest, the two of you have chosen different levels for y equals 0 in this problem. Which of the following quantities will you and your friend agree on? The potential energies values you will not agree on, because these are really affected by your reference. Now the skier's change in potential energy, of course, is going to be the same in both cases, and the skier final kinetic energy is going to be the same, because based on conservation of energy, the change in the potential is going to be the change in the kinetic, and then this will not affect the skier's final kinetic energy. Okay, the gravitational potential energy depends. Here we are talking about the individual values, which means when you are going to calculate the initial and the final. Okay, the difference is not. And here I have two paths led to the top of a big hill. One is steep and direct, while the other one is twice as long but less steep. How much more potential energy would you gain if you take a longer path? Remember the equation that we are using for UG, it is mg times y. Then it depends just on the vertical distance. Okay, then the vertical position changes by the same amount in each case. The gain in potential energy is the same. Now, here I will say also one of the characteristics we mentioned for what we say like the conservative forces is that their work doesn't depend on the actual path. And here we have 3 balls of equal mass starts from rest and roll down different ramps. All ramps have the same height. Which ball has the greatest speed at the bottom of its ramp? And of course the same speed, because it depends, like taking what is called conservation of energy. You're going to say mgy equal, or mg delta y should equal 1/2 mv squared, then the speed is going to be the same, because they initially have the same gravitational potential energy that depends only on the vertical height. And then I will say is going to be 1/2 mv squared, the same for both. And here I will say We have also another conceptual question. Paul and Kathleen starts from rest at the same time on frictionless water slides with different shapes at the bottom, whose velocity is greater. We said that the vertical distance is not going to change for both, then they're going to have the same. And of course, it's a very simple problem that we did solve, and we will solve more like this one. Okay, mgy or mgh equals 1/2 mv squared, then same height means the same velocity. But let's say here starts from rest at the same time in frictionless water slides with different shapes. Who makes it to the bottom first? Then this is really here. If you look at the pictures, we're gonna find that Kathleen is gonna make more, like is gonna be lower than Paul, which means she is having more speed, more velocity, and she's always have a larger velocity during her dry, and therefore she's gonna be the one who's gonna win the race. Okay, also here we're gonna deal with another type of potential energies, which is the spring or elastic potential energy. I will use for it US. Now, we did cover this before, and we said, like here, I have a work done by a variable force, and that variable force is the force of a spring. And then I was able to calculate that the work done here is going to be 1/2 kx squared. And remember, we have that valid even for any, I will say, potential energy function. The work done is going to be negative the change in US. Now, what if we have problems that we have elastic forces, which means I have a spring? Then I can, of course, now include 3 types of energy. If I don't have any change in the vertical, then I will say only I'm going to include kinetic and potential because the gravitational is not changing. Then I will say 1/2 mv1 squared plus 1/2 kx1 squared equals 1/2 mv2 squared plus 1/2 kx2 squared. And if there is a change in a vertical position, then now the gravitational potential energy is going to change, and then I need to include a term that is going to be related to kinetic gravitational potential energy. I like to write this as Ki plus USI plus UGI should equal K final plus US final plus UG final. This is when I have all conservative forces, and I might have all of them there. Now, in the case when I have non-conservative forces, like I have a pull, I have a push, or I have friction most of the time, we're going to say Ki plus USI plus UGI plus work by non-conservative should equal K final plus US final plus UG final. And I will say this is the most general form of conservation of energy. I like always to use charts, and this is the reason what you will see me sometimes like to be more, I will say, aware of what I have. I will draw something like this. Let me show you what I will do here. And sorry. This is I final, and this is K. This is my Ki, this is my K final. This is my UG, and of course all in joules. And this is, this is gonna be my UGI, and this is my UG final. And this is US in joules as well. And this is USI, US final. And then here, work by non-conservative is going to be the force times the distance cosine the angle. All right. Now, that term here, I can have it. Most of the time, I will have friction. Then this is going to be the force of friction, usually Fk times the cosine 180. And this is the reason why it's going to show up as negative. Okay, and of course, we will not have that cosine. All right, then this is the most general form of the conservation of energy. Okay, how does the work required to stretch a spring 2 centimeters compare to the work required to stretch it 1 centimeter? It's very clear that when I have it like 1 centimeter is going to be, let's say, x1 squared. And then when I double that to x1, then this is going to be 1/2 k4 times x1 squared, which means this is going to be 1/2 kx1 squared, and here it is times 4, of course, because it is a square. It depends on the x squared, not on x itself. Okay, this question is talking about the vertical spring, and we will ignore here the mass of the spring, whose spring stiffness constant is 950 Newton per meter, is attached to a table, and is compressed down 0.150 meters. First part, what upward speed can it give to a 0.3 kilogram ball when released? B, how high above its original position, spring compressed, will the ball fly? Okay, I have recorded here the mass and K, and I just provided a very simple sketch. The first one, of course, like you need maybe to have your hand pressing that spring with the ball so that it will be compressed, and it is compressed 0.150 meters. I did choose to have my y, my UG equals 0 here, where my y is going to be 0. And this is the reason why I considered my yi here to be negative 0.150, because it is below my reference. My final, this is for part A, is going to be when that ball is going to reach that y equals 0, okay, then the spring is not stretched at all, it's not compressed at all, it's not stretched also, and all the elastic potential energy that was initially stored, it is converted into kinetic energy. All right, and of course, I need to include like the elastic potential energy was converted into gravitational potential plus kinetic. Now here I will include all the three. I don't have my non-conservative here is 0. Then I will say, okay, this is my table. Simply here, you can even just without going to the next tab, is you can eliminate the values where they're gonna 0, and when it will not be stretched nor compressed or stretched, this is gonna be 0. Then I will say mgyi plus 1/2 kxi squared or x1 squared should equal my mg 1/2 mv2 squared. And then I can finally find my velocity as 8.26. Of course, for the sake of significant figures, I will change it into 8.3. Now, after that is a free fall problem. When it will reach the maximum height, you're gonna say that all the kinetic is gonna be converted into gravitational potential energy, and you will be able to find that Y3 is gonna be 3.5 meters. Now, the question is asking about how high above its original position will the ball fly. Then I have calculated this from here to here to be 3.5, isn't it? 3.5, yes, meters. And I need to include that additional, okay, 0.15. And this is the reason why I said Y3 minus Y1 is going to be 3.5 minus 0.15. And this is going to give me 3.65, which is 3.7. Now, the work done by non-conservative, as I said, we have a non-conservative force. We need to include it. And the work done by it is going to be converted into heat. And we will not be able maybe to reuse that energy. And we're going to say that the energy is dissipated. But the energy as a whole, because remember, and we will study this, like heat, it is one form of energy, then the total heat, the total energy is going to still be conserved. Now, friction does not dissipate total energy, just the mechanical energy. And the mechanical energy does not include thermal energy, which comes from friction. And this is the reason why I need to include it here. Then I will say, also, I'm talking in general, this equation can be used even if my force that is non-conservative, it's not only friction, it can be any type of forces. In this problem here, we have conservative force. It is friction again, but it is water resistance. Now you throw a ball straight up into the air. In addition to gravity, the ball feels a force due to air resistance. Compared to the time it takes the ball to go up, the time it takes to come back down is gonna be greater, because now we are going to have two situations. Now the friction is gonna make the ball continuously losing mechanical energy, and because of that it will have less kinetic energy, which is gonna affect the speed, and then it's gonna take more time down. Now this is one of the problems in the problem solving, like the roller coaster that we did before. A problem related to reaches a vertical height of only 25 because of the friction. Okay, and it traveled a distance 400 meters. Estimate the average friction force on the car whose mass is 1,000 kilograms. Now the work done by friction is going to be minus mg times delta y, because I can simply say here, let me write this here on the side, EI plus work done by non-conservative should equals E final. And I will say here, then EI minus E final equals the work by non-conservative. And it was stated that here V is 0 and also V equals 0 here, no springs. Then I will say this is going to be mgy I minus mgy final should equals work by non-conservative. And I will be able to calculate what is really the work done by non-conservative. And this is gonna be, let me just here, I will say this is my, I did a mistake here with the minus. Yeah, I was looking at it and I want to find it. Okay. Here, work by non-conservative. This is where the minus is going to come. Okay. And that is going to be mgy final minus mgy initial. And since y final is less, remember we said like the friction force is going to make the mechanical energy less, and this is the reason why we are gonna get that as negative number. And then I have calculated here the work done as negative 147,000 joules, and from that I can calculate what is the force of friction by just dividing by the distance. And for the sake of significant figures, I will round it to just to sig fig. This one here, it is a horizontal spring. I have a block that has a mass of 5 kilograms and is attached to a horizontal spring with spring constant K equals 4, 10 to 2. This one is 10 to 2 in Newton per meter. The surface, the block rests upon, the surface the block rests upon is frictionless. If the block is pulled out to x0 equals 0.05 meter and released, find the speed of the block when it first reaches the equilibrium point. What I have here, I listed my masses, my mass, my K. This was my initial when my spring was stretched 0.05, and then it will go back to the equilibrium here. This is my x equals 0. This is the equilibrium. I can say here, these are conversions of energy when all the elastic potential energy will be converted into only kinetic energy. From that, I can derive my equation for the final velocity to be v final squared k over m xi squared, and then I was able to calculate my v final to be 0.447 meters per second. In the second part, find the speed when x equals 0.0250 meters. And always, I think it's a good idea maybe to have kind of, understanding if I'm going to have more speed or less speed based on, that sharing between the kinetic and the potential. Remember in the first one, like my elastic potential energy was all converted into kinetic. In this second part, my initial elastic potential energy was partially converted into kinetic, and I still have another part which is still elastic potential energy. And this is the reason why I will write 1/2 kxi squared will equals 1/2 kx final squared, which is x final here, it is 0.025, plus 1/2 mvx squared. And from that, I can get my Vx to be 0.387 meters per second. Obviously, it is less than the one in part A because now I still have elastic potential energy stored in the spring. The last part, we're going to repeat part A, but we are going to assume we have friction, and we have a mu k that it is 0.150 on that surface. I will say here, I like maybe to do my chart here just to show you how I'm using it. And then here I will say my K kinetic energy was initially 0, and then it will reach 1/2 mv final squared. This is a horizontal situation where there are no changes in the vertical position, and this is the reason why I'm going to get 0, 0 for initial and final gravitational potential energy. For the elastic potential energy, initially my spring was stretched by xi, and then finally it will be 0. Here I am calculating the work done by non-conservative. And remember, okay, the force of friction, Fk, it is mu k times the normal. And in this case, mg equals the normal. Then this is the reason why I have it mu k times mg. Also, d here equals xi because my object was moving. I don't like to use like here xi maybe like for the friction because you are used to this equation having d in it, and the minus I have it because of the cosine 180. What I can do is I can add all the terms on the first row. Sorry. Then it's going to be 1/2 kxi squared minus mu k mgd equals 1/2 mv final squared. And then I can rearrange my terms, and don't forget to take the square root of this number, which is and you will find that it is 0.230 meters per second. I want you to look at this question more than one time and also now compare when this is, remember again, the presence of that frictional force, which is a non-conservative force, did hit the mechanical energy, then my mechanical energy was decreasing, and this is the reason why I will get a smaller number for the velocity than part A. Now, I will say the curve of a hill or a roller coaster itself can be a plot of the gravitational potential energy. And I can get the potential energies from this. Okay, then I have on my y, UG, and I have here what is like, you know, the X or Y or whatever, like I'm talking about. And every time you're going to say this is your Y and this is your K. But your total is going to stay the same, right? Your total is going to stay the same. Okay, now, okay, then this is, if my ball was released from here, it would reach a maximum here. Now, these points here, where my E, my total energy equals UG, and my kinetic is 0, these are, we call the turning points. After that, the kinetic energy will, because now here the velocity did reach a value of 0, then after that I will say it's going to reach a negative value. Now, this is really the potential energy curve for a spring, because we have plotted, and then if this is really the maximum stretch, I would say, or compression, then this is the maximum energy, and then at the end points, which are the turning points, I will have E, total mechanical energy, equals US here, and then at this point my US will be 0 and all is going to be kinetic. At any point you have, this is U and this is K. Okay, here this is the last problem. Here I have an object moves along the x-axis subject to the potential energy shown in the figure. The object has a mass of 1.1 and starts at rest at point A. Then we know that at point A it has 0 kinetic energy, and UGA equals 10, then the total mechanical energy is 10. At point B, of course, we know that UGB from the diagram, it is 2, then, and E, of course, is 10 again, then K is going to be E minus UGB, which is going to be 10, minus 2 is going to be 8, and that equals to the 1/2 mvb squared. From that, you can get your velocity as 3.8 meters per second after you consider the significant figures rules. I'm going to repeat the same calculation at C and D, and this is going to be 2.7 and 3. The last question is asking about what are the turning point for this object. Remember, I said when UG was 10 joules and K was 0, this is the first one, which was, I think, point A, right, in the diagram. And there is another point where UG equals 10 joules and K equals 0, which is point E. Then A and E are really turning points for this object. This is summary of chapter 8. Conservative forces conserve mechanical energy. Non-conservative forces convert mechanical energy into other forms that we cannot reuse again. Conservative force does zero work on any closed path. Work done by a conservative force is independent of the path. Examples on conservative forces, gravity and spring. Examples on non-conservative is friction. Work done by non-conservative force on closed path is not zero and depends on the path. Non-conservative forces, examples, friction, air resistance, tension, pulling, pushing, all these. Energy in the form of potential energy can be converted to kinetic or other forms, and the work done by conservative force is the negative of the change in its potential energy. The gravitational potential energy we use for it, I use for it UG equals mgy, and for the spring US equals 1/2 kx squared. Mechanical energy is the sum of the kinetic and the potential energies. Then I will say is going to include US plus UG. Non-conservative forces change the system's mechanical energy, and the work done by conservative forces equals the change in the system's mechanical energy. And finally, we have the potential energy curve. It is giving us information about U versus position, and we will be able to calculate K's, velocities, and also find the turning points.